In 1928, a young man said a single sentence that nearly drove Heisenberg mad. He said that particles with negative energy exist in the universe. After hearing this, Pauli reportedly declared that he was giving up quantum physics to write novels. Heisenberg went even further. In a letter to Bohr, he wrote, "I think the current situation is utterly absurd. I am almost desperate enough to change my field." But what was even more terrifying was that 4 years later, this insane prediction was confirmed. At Caltech, Anderson captured a bizarre track in a cloud chamber. It looked like an electron, but with the opposite charge. This was humanity's first discovery of antimatter. And it meant that at the birth of the universe, out of every 1 billion particles, only one survived. All the others annihilated. The fact that you and I exist is itself a 1 in a billion miracle. So who exactly was this young man who threw the entire physics community into chaos? His name was Paul Dirac, a 26-year-old British physicist. At the time, he stood on lecture halls in Germany, teaching in an extremely peculiar way. Physicist Eugene Wigner once said that Dirac lectured as if he were reading a technical manual, with absolutely no emotional fluctuation. And yet it was this seemingly wooden young man who proposed a theory that all the giants of physics found impossible to accept. What was Dirac working on? He wanted to unify Einstein's relativity with quantum mechanics. In 1905, Einstein proposed that famous equation, E equals mc squared. This equation tells us that mass and energy can be converted into each other. But here's the problem. When you take the square root of this equation, you get two solutions. One corresponds to positive energy, the other to negative energy. In classical physics, negative energy simply does not exist. So everyone ignored it. But Dirac didn't. He realized that once you combine relativity with quantum mechanics, the negative energy solutions can no longer be discarded. In the quantum world, particles can move like waves, exist in multiple places at once, and refuse to follow common sense. If negative energy particles truly existed, what would happen? An electron could release energy endlessly, falling into ever lower negative energy states, until it dragged the entire universe down with it. This is why Heisenberg said, "This was the most tragic chapter of modern physics." The theory was logically flawless, but in reality, it was a catastrophe. Pauli simply couldn't take it anymore. He actually wrote a letter saying he wanted to abandon quantum physics and switch to writing utopian novels. Imagine it, the greatest minds at the peak of human intellect, driven to consider changing careers by a 26-year-old newcomer. That's how desperate things felt. But Dirac did not give up. In 1928, he derived a new equation, later known as the Dirac equation. This equation perfectly combined relativity and quantum mechanics, and could accurately predict the behavior of particles moving at high speeds. Why is gold golden? Because the gold nucleus has 79 protons, which strongly attract the electrons, accelerating them to near the speed of light. The ordinary Schrödinger equation can't handle this, but the Dirac equation can. Why is mercury liquid at room temperature? For the same reason. Once again, the Dirac equation gives the correct answer. But this equation also came with a side effect. It predicted a particle that had never been seen before. A particle identical to the electron, with the same mass but opposite charge. Dirac called it the anti-electron. At the time, no one believed such a thing existed. They thought it was just a mathematical game. The turning point came in 1932. At Caltech, a postdoctoral researcher named Carl Anderson was studying cosmic rays. Cosmic rays are streams of high-energy particles that strike Earth from outer space, bombarding our atmosphere every moment. Anderson used a device called a cloud chamber to observe them. The chamber was filled with supersaturated vapor. When a charged particle passed through, it left behind a white trail, like a condensation trail left by an airplane in the sky. One day, Anderson noticed a strange track in a photograph. It curved in the opposite direction from an electron. When placed in a magnetic field, it looked like a positively charged electron. At first, Anderson thought it might be a proton, since protons are positively charged, but that couldn't be right. A proton's mass is 1,836 times that of an electron. It couldn't have traveled that far through air. The track showed that this particle was extremely light, almost as light as an electron. Anderson stared at the photograph for a long time. He realized he might have discovered an entirely new particle. He named it the positron. He even tried renaming the electron the negative electron, but that name never caught on. In September 1932, Anderson published his discovery in Science magazine. The world was stunned. When Anderson discovered the positron, he had no idea about Dirac's prediction. He was an experimental physicist, working quietly in the lab, completely unaware of the latest developments in theoretical physics. And Dirac? He had predicted the anti-electron back in 1928. but even he wasn't fully convinced it was real. When Anderson's paper was published, Dirac probably thought to himself, I just calculated this casually, and it turned out to be true. This is one of the most classic accidental discoveries in the history of science. Anderson wasn't trying to test Dirac's theory. He was simply observing cosmic rays, and accidentally collided with antimatter. In 1936, Anderson won the Nobel Prize in Physics for discovering the positron. He was only 31 years old, making him one of the youngest Nobel laureates in history. But the problem wasn't fully solved. The nightmare of negative energy particles still loomed. If positrons could really fall into negative energy states, the universe should have collapsed long ago. So Dirac proposed an even crazier idea, the Dirac Sea. He said that the vacuum is not empty, but an infinitely deep ocean, filled with negative energy electrons. All these negative energy states are already occupied, like a movie theater completely full, with no empty seats left. That's why ordinary positive energy electrons have nowhere to fall. They are forced to remain in positive energy states. So what is a positron? Dirac said a positron is simply a hole in this sea. When a negative energy electron is excited out of the sea, it leaves behind a vacancy. That vacancy behaves like a positively charged particle, which is the positron. When a positron meets an electron, the electron falls back into the sea, filling the hole. Both particles disappear simultaneously, releasing energy. This process is called annihilation. Can you imagine it? The vacuum beneath our feet is actually an invisible ocean of electrons. We are like bubbles floating on its surface. This theory sounded completely insane, yet mathematically, it was perfectly consistent. Many top physicists at the time felt it was absurd, but they couldn't find a flaw. Later, in 1941, Swiss physicist Ernst Stueckelberg proposed a more elegant interpretation. He suggested that negative energy particles, moving backward in time, are equivalent to positive energy antiparticles, moving forward in time. It sounds like science fiction, but mathematically, it works. A few years later, the brilliant physicist Richard Feynman turned this idea into the famous Feynman diagrams, used to describe particle interactions. In Feynman diagrams, antiparticles are simply particles traveling backward in time. Today we know that every particle has a corresponding antiparticle. Electrons have positrons, protons have antiprotons, neutrons have antineutrons. They have identical mass, but opposite charge. When a particle meets its antiparticle, they annihilate, converting all their mass into pure energy, released according to E equals mc squared. This leads to a cosmic mystery. Why is our universe made of matter, instead of antimatter? In principle, the Big Bang should have produced equal amounts of matter and antimatter. If that were the case, they would have annihilated completely, leaving behind only photons. No galaxies, no stars, no us. But we exist. This means that in the very first moments of the universe, there was just a tiny excess of matter over antimatter. Scientists have calculated that, for every 1 billion matter-antimatter pairs, there was one extra matter particle. That single surviving particle made it through the annihilation war, and went on to form all the matter in today's universe. You, me, Earth, the Sun, the Milky Way, all come from that 1 in a billion asymmetry. Why does this asymmetry exist? This is one of the greatest unsolved mysteries. In modern physics, scientists have proposed many theories, such as CP symmetry violation and leptogenesis. In 2024, the Large Hadron Collider at CERN is conducting a new round of experiments, trying to uncover the origin of the matter-antimatter imbalance. They have even built a dedicated antimatter trap, using magnetic fields to suspend antihydrogen atoms in midair and study their properties. Antimatter is not just a theoretical concept, it has real-world applications. PET scans in hospitals rely on antimatter. Doctors inject patients with tracers containing radioactive isotopes. These isotopes emit positrons. When positrons meet electrons in the body, they annihilate, producing 2 gamma rays traveling in opposite directions. Detectors capture these rays and reconstruct a three-dimensional image of the body, helping diagnose cancer, heart disease, and more. In 1933, Dirac won the Nobel Prize in Physics for discovering new productive forms of atomic theory, sharing the honor with Schrödinger. He was 31 years old when he received the prize. His reaction was remarkably calm. Just like everything else he did, he showed almost no emotion, and simply said, "Thank you." Dirac's personal life was equally dramatic. In 1934, his friend Eugene Wigner introduced him to his sister, Margit. The two of them were like matter and antimatter. Dirac had almost no capacity for emotional expression, quiet and withdrawn. Margit was warm, energetic, and extremely talkative. Dirac knew he lacked emotional expression, yet the marriage turned out to be surprisingly happy, lasting until Dirac's death in 1984. A mutual friend once summed it up perfectly: he gave him status. He gave him life. So yes, in the universe there are particles and antiparticles that annihilate when they meet, but there are also people like matter and antimatter, who create perfect balance when they come together. Back to that decisive moment in 1932, when Anderson took that photograph. He had no idea that the seemingly ordinary white track would change humanity's understanding of the universe. The discovery of antimatter did more than confirm Dirac's wild prediction. It opened a door to an entirely new world. It told us that the universe is far more symmetric, more subtle, and more mysterious than we ever imagined. Even today, scientists continue to ask, where did that 1 in a billion asymmetry come from? Do antimatter galaxies exist somewhere in the cosmos? Can we harness antimatter as the ultimate energy source? Perhaps one day, the answers will be discovered by accident, just like that moment in Anderson's cloud chamber. And all of it traces back to 1928, when that quiet young man stood on a podium in Germany and spoke a single sentence.